Okay, hi everyone. Thank you for attending our SNAPP seminar today. So today we're very happy to have Minshuo from Northwestern University talking to us about an optimization perspective on guidance for fine-tuning diffusion models. So for a bit of background, so Minshuo is an assistant professor with the Department of IEMS at Northwestern University. He was an associate research scholar with the Department of ECE at Princeton University from 2022 to 2024. He completed his PhD from the School of ISE at Georgia Tech, majoring in machine learning. His research focuses on developing principled methodologies and theoretical foundations of deep learning, with a particular interest in generative models, including diffusion models, foundations of machine learning, such as optimization and sample efficiency, and reinforcement learning. So Minshuo, you can take away, and you have about 1 hour.
All right. Thank you. Thank you for this very kind introduction. And it's my great pleasure to see everyone online. It's my first time doing this. Today I'm talking about an optimization perspective on guidance for fine-tuning diffusion models, which is falls into the large area of generative AI. And this is a joint work with a couple of wonderful collaborators. Well, nowadays people might be already enjoying the power of generative AI, but I will say this kind of power is brought possible by the millennium growth of AI starting from this century. At the first maybe 20 years, people are focusing on something I terminated as discriminative AI, where people try to do network architecture innovations, and the task is typically some classification or regression, which tries to describe some properties of the data set. And in 2013, there's a model which called a variational autoencoder, which strikes a start of a new era, which I terminated as deep generative AI era. And there are a couple of very famous models developed along the past 20 or 10 years. And nowadays, people are enjoying the power of deep seek, and this figure might be very familiar to every one of you. And I guess I'm using ChatGPT on a daily basis. So this type of shift in the AI models and AI tasks also indicated a shift in the training paradigm of those very large models. In the discriminative AI era, people try to train on a large collected data, labeled data set. And on these labeled data set, people have kind of this image is a cat or that image is a dog. And the goal is try to, if I give you a new image, then what this image describes, for example, a cat or a dog. So this is kind of like a task-specific training where the network is trained on this particular task. However, in the generative AI, people will try to collect massive external data. For example, collection of passages from books, collection of web pages on the internet. And the people will train a large, massive foundation model on those data sets. And the extremely difficult part of this modeling is the massive external data does not have any label. So it's kind of like the massive foundation model is trying to collect all the information that this model can see. Well, after the training of this massive foundation model, people will try to fine-tune this massive foundation model towards specific tasks. And this can be achieved by using proper prompting or using a large collection of methods called fine-tuned methodologies, or aligning the massive foundation model towards specific tasks. And those tasks are quite diverse, like code generation, like classification, or like mathematical reasoning. So our focus today will be trying to understand how can we fine-tune a large, massive foundation model so that it can align very good with some downstream task objectives. So to give you some real working examples of fine-tuning, here I listed 4 applications. Number 1 is ChatGPT, and of course, this is a very familiar example to every one of you. And the last 3 examples are some applications biased towards the usage of diffusion models, which is the topic of today. So Sora is actually a video generation model, which can generate photorealistic and high fidelity videos. And RF diffusion is a molecule generation model which can generate molecule structures that will fit into a base of a larger molecules. So these models are not possible if we just train it on a large collection of unlabeled data, because it will not pay attention to any of the structural informations. And the fourth example is a decision diffuser, which people use diffusion models to do policy learning in reinforcement learning and control problems. These learning will be made possible when we fine-tune on a large collected offline data set. So in terms of methodology, there's actually a large collection of methodologies. For example, people can use adapters to change slightly a bit on the massive foundation models. And the people can also use LoRa, supervised fine-tuning, reinforcement learning with human feedback, and also distillation, all sorts of different type of methods to do the alignment of a massive foundation model aligned with a task objective. However, those methodologies are actually heuristics focused, and they often provide very limited theoretical guarantees. So in this talk, I will try to provide you with a very simple and computationally very cheap and also theoretically provable methodologies that can possibly align a pre-trained diffusion model with an underlying task objective. So I have mentioned the diffusion model several times, and the diffusion model is actually a one paradigm in the generative AI models. So the objective of diffusion model is to generate new data, just as the middle box shows. So the starting point of this generative model is starting with a noise distribution. This noise can be a Gaussian distribution, can be other very easy to sample noise distributions. And through some transformation, it will generate new data. And this new data will try to copy many of the important characteristics in the training data. For example, here, Mona Lisa is just appearing in a very different artistic style. However, we can easily recognize that this is an image of a Mona Lisa. So I view diffusion model consisting of two important components. Number one is the modeling part. And in the modeling part, we are using a large collection of data points so that we can learn some underlying distribution of those data. For example, I just denote the underlying distribution as P of the data. And sometimes we can also work with conditional distributions. For example, we just want to model the data of cats, or we want to model the data of dogs. And here, Y can be the label of your data. And more broadly speaking, this Y can be any conditional information we want to impose on the data set. And the second part is the sampling part. So after we model the data using a massive collected data set, we want to generate new data. So we can view this generation as a sampling problem. We want to sample our data from the learned distribution. Again, here distribution can be P of X or P of X given Y. And here Y is possibly another conditional information we want to impose in the generation. So for example, we trained our generative model on images of dogs and cats, and then we want to generate images of dogs, or even like go beyond the cats and the dogs to generate other animals. And the very famous language models are falling into this paradigm by describing the language using a autoregressive model and then generate new text information using the autoregressive manner again. However, diffusion model works in a slightly different manner. For the modeling part, we are using the diffusion process. And for the sampling part, we are using some denoising process. And the diffusion process basically says, okay, we gradually forget about our data information by adding noise to the data. And for the denoising process, we start with pure noise and hope to remove the noise to reproduce our data distribution. So we will get to details of this diffusion and denoising process later. However, this just provides you an overview of how diffusion models try to generate the data. So this is a slide that I kept collecting, and nowadays this slide is actually quite messy. First of all, where people try to show that diffusion models in some unconditioned generation manner can beat previous state-of-the-art models like GANs and achieve record-breaking performances. And this figure is collected in year 2023, and we see that this benchmark list consists of models using diffusion models quite frequently. Well, then people try to expand the application domains of diffusion models beyond image generation. For example, like audio generation, language model generation, and video generation. So starting from year 2023 and 2024, there are actually more and more fancy applications of diffusion models and striking the success of fine-tuning large, massive trained diffusion models. For example, diffusion models are quite helpful in protein structure generation. They are helpful in reinforcement learning systems, and they are helpful in generating photorealistic portrait that allows many editing requirements. And nowadays, diffusion models can be a real-time game engine, and it can also use in language generation. So I hope this try to convince you that there's a shift of using diffusion models from the pre-trained methodologies to using fine-tuned methodologies and to enable many of the fancy applications. So the outline today is we will try to introduce diffusion models briefly, and then we will talk about how can we model the fine-tuning tasks of diffusion models using conditional languages and develop the concept called guidance. And then we will provide how can we choose or design guidance so that it can be computationally scalable. And it can also provide you many alignment guarantees. And lastly, I will talk about some future directions. So I will pause a little bit to see if there's any questions. Okay, cool. So let me begin with a very brief introduction to diffusion models. So this is kind of like a recap of what we have introduced in the previous slide. So the diffusion model consists of two components. Number one is the modeling component, and the number two is a sampling component. However, in the previous introduction, we kind of like view these two as a separate modules, but indeed these two modules are connected by some magical quantity called the score function. And the score function is something that we will learn from our massive collected data, and the score function is typically parameterized by a network. And the network structure can be a U-network or a transformer nowadays. So if we dive deeper into modeling and sampling processes, we will get to a forward and backward processes. So the forward process is used for modeling the data. And the idea of this forward process is just to try to add noise to our data distribution so that we can gradually forget about our data distribution. So mathematically speaking, the forward process can be written as the stochastic differential equation dxt equal to minus 1/2 xt dt plus dwt, where wt is a Brownian motion. So if you are not familiar with the stochastic differential equation language, no worries. We can just understand this process looking at the bottom line of figures. So there are two things happening simultaneously. The first one is we will compress our data magnitude towards 0, which means we move our data point towards the origin of the axis. And simultaneously, we will add larger and larger Gaussian noise to each data point, which is depicted by those blue shaded area. So if we run this process for an infinitely long time, we will see that the data distribution will be transformed into a perfect Gaussian distribution. And this is more clear if we look at the transition of the data density functions. For example, we start with a data distribution that has a density function of 2 peaks. And as we compress the data magnitude and adding noise to the data, we will see the blue curve depicting the density functions gradually merge together. And then we get a density function that can possibly has only one peak. And finally, the density function will behave very nicely as a Gaussian density function. Good. So this process basically is relatively intuitive because we are compressing our data magnitude and adding noise to the data so that we can forget about our data distribution. And this is the idea diffusion comes from. But this actually has nothing to do of how can we generate new samples. But this actually has a indication. So suppose we can travel reverse in time, which means we can start with the approximate noise distribution, and we travel through this adding Gaussian, travel back through this adding Gaussian noise process. Then we can possibly get a data distribution. But how is that possible? Well, mathematically speaking, this is possible if we look at some like classical results in the stochastic calculus. But let me just try to provide you a very high-level idea. So we have a time machine that can travel backward in time, and this time machine is something called gradient log pt of xt. And here pt is the marginal density function of the data distribution when we travel through the forward process. The correspondence between the forward and the backward processes are written in the following two equations. So the backward process is nothing but just adding one additional drift term, which is our time machine, to the forward process. And this time machine has the name score function. The correspondence between forward and the backward process is depicted in this figure. So the forward process starts with a data distribution and transform data distribution into noise distribution. The backward process starts with noise distribution and transform into a data distribution. So the correspondence is depicted by those broken arrows. So at the corresponding time, the marginal distribution of the forward process will be the same as the backward process. And in this case, backward process achieved the generation of new data points because we can transform our noise distribution into data distribution. So there is actually a little bit nuance in this correspondence because we don't know our time machine, which is the score function. So the training of the diffusion model is actually estimating this score function. And the estimation is using the forward process because the backward process is responsible for generating new data, which is often the case that we will use. And conceptually, the training of the diffusion model is try to match our score neural network, which is denoted as this blue quantity S. And the target of this S is try to replicate what is the score function, gradient of log pt. And apparently this is just a conceptual loss because this score function is unknown to us. And we have a very nice transformation on this training loss so that we can efficiently implement this training loss. Okay, so let me see if there's any questions about this very basic introduction to diffusion models. Okay, good. All right, so this is kind of like saying, okay, if I give you a large collection of data and I forget about or I neglect anything that may be associated with the quality of their data, then I can generate new data points using this training framework and then follow the backward process to generate new data. But what if we have some like additional information on your data point? For example, we just want to impose some label information, and this label information can be generally described as some like a prompt input. I want to generate a figure that is describing a raccoon washing dishes. And here, why is actually this prompt input? And we want to generate an image that can align with this prompt input, just like the last image of this line of image showing. And another example is if we want to generate some protein molecule structures, we want to impose some biochemical properties so that this generated protein structure can be really tested in wet lab. So we here take Y to be biochemical properties, and we want to generate molecule structures satisfying certain biochemical properties. Those are really working examples, and we are transitioning from a point from generating data in an unconditional manner to generating data with conditional information. And generating conditional information in diffusion models is not very difficult. And conceptually, we can just replace the previous score function by this conditional score function. And the difference between this conditional score function to the unconditional score function is we introduce this label information, y equal to dog, for example, into the distribution. And here we keep our label information y all through all the transformations on x. Here we see that the distribution now becomes a conditional marginal distribution, p of x given y. And in order to get this conditional score function, we allow many of the choices on the label information y. It can be text prompts, it can be reward values, it can be labels. So the key is actually how can we scalably estimate the conditional score function? But let me elaborate a little bit on this claim. So compared to the unconditional score function estimation, we usually have a large number of data points. However, in many of the conditional generation tasks, the labeled information is really limited. For example, we want to generate an image of dogs, or we want to generate an image of a very a rare animal, then the existing image of that animal could be much, much less compared to the unconditioned samples. So there's a very incentive to do conditional generation based on the training of the unconditioned models. And this is something that we will talk about by introducing guidance to start with a pre-trained large unconditioned diffusion model so that we can generate conditional data. Okay, so before I move into more detailed introduction of the conditional scores and the guidance, are there any questions? Okay. All right. So here is a little bit like mathematical exposure on how can we view the conditional score functions as a adjusted term based on the unconditional score function. So we can use Bayes' rule to write this conditional score pt of xt given y into a ratio using the full probability or the joint probability between x and y divided by the distribution of y. And taking log and then taking gradient with respect to x will cancel the log pt of y. And finally, we get the last line, which says the conditional score function is the unconditional score function plus some adjusted term. And this adjusted term, we will call it guidance. To get you familiar with the guidance, let's just think of y as a label. And this probability of label given our data is actually a classifier. So that's why there's a methodology called classifier guidance, which says, okay, once I give you a pre-trained score function, I can externally train a classifier and then add the gradient of the logic of that classifier to adjust the unconditioned score function so that we can generate samples according to our label. But this classifier guidance is actually limited to y being a label. Suppose let's consider if y is a real valued reward, or if y is any very abstract prompt information. Then how can we incorporate this, or how can we find this guidance term? And this is the topic of today. In the existing literature, there's some like maybe computationally a little bit heavy, and also those methods does not enjoy strong theoretical guarantees like classifier-free guidance or some universal guidance methods. So before I introduce some of the guidance design and also how can we derive theoretical guarantees on incorporating those guidance, let me try to explain what are the roles of guidance. There are actually two roles. Number one is I term it as to optimize. And to understand this role, we can abstract many of the task-specific objectives as a reward function. And this reward function can incorporate many of the informations. For example, we can consider generating images of certain labels. And this reward function can be the matchness of our generated samples with the corresponding label. So I claim that guidance is to optimize this abstract reward function by generating new solutions. And we understand this as depicted in the following figure. So on the left, we have a unconditioned diffusion model, which can generate, for example, images. And here I choose the reward function to represent if the figure is colorful or not. So as we can see, as the reward value increases, there are more red, green, and all sorts of colors in the image. So the unconditioned diffusion model can generate all sorts of images. Maybe these images are colorful, or maybe those images are not. And with some type of guidance, I denoted as this red term G here, we are shifting the generated distribution towards a distribution that's centered around the high reward area. So with this guidance, we can generate new images, and those images tend to have really colorful footprints. So we will see that those astronauts and those cats are having more and more red, green, those type of like really high contrastive colors. So this actually says, okay, by imposing the guidance, we are generating new samples that can potentially optimize the abstract reward function so that we are better aligned with our downstream tasks. And there's actually another role of the guidance. So if we just focusing on achieving a large reward in the generation, then possibly we can generate something that's already out of our recognition. And this is something recognized as the reward collapse. So I term this requirement of guidance as they need to preserve data fidelity. And we can see from the following example, we generate the upper row and the bottom row figures. And those figures are actually of relatively high reward. So those numbers, 0.05, 9.05, 8.82, blah, blah, those things are just the abstract reward of those images. And we see that the upper row figures even achieved a higher reward value compared to the lower row figures. But we cannot recognize what are the image in the upper rows. Although we labeled it as a snail, but it's just some kind of like light and dark shades. So most of the time, we want to generate high reward samples, but we also want to preserve the data structures so that people can recognize what is the generated image or what is the generated data. With these two rows, we can actually formulate the fine-tuning of diffusion models with guidance using a generative optimization perspective. And here I just try to connect this generative optimization perspective with the traditional optimization problem. Suppose we have an abstract reward function f, and we want to try to maximize or optimize this abstract reward function by finding its solutions x star. So in the traditional optimization perspective, we need to handle like a complex landscapes, and there's actually some like implicit constraints on the generated solutions x star, which is the data fidelity. We want to generate an image that makes sense to human eyes. So this can be considered as a very challenging problem because of the difficulty of describing what is data fidelity and also the unknown landscape of the abstract reward function. So we use this generative idea to formulate this problem as a sampling problem. So we want to directly sample our solution X from a conditional distribution, and that conditional distribution is the distribution underneath those samples that make sense to human eyes or to our perception. And the condition I impose here is, for example, the generated sample can achieve a reward that has value A or larger than A or other type of conditional informations that we desire. So compared to the two challenges that's listed on the left-hand side, using this generative idea actually considers two different challenges. Number one is how can we learn the conditional distribution? And the second one is corresponding to the first one is how can we design guidance so that we can start with a pre-trained unconditional model so that we can generate the samples with those conditional information. Okay, so let me also pause a little bit to see any questions here. Okay, cool. Well, so in the next two sets of results, I will try to provide you with ideas of how can we solve this generative optimization problem using conditional diffusion models. And in the offline setting, I will try to understand what is the proper way to impose the conditional information. And in the online manner, we will try to develop some computationally cheap guidance terms that can be added directly to the pre-trained score function. So the setup of this offline problem is, suppose I give you a data set, and we want to generate new solutions X. Well, the data set consists of two parts. The number one is the unlabeled part, which is the majority of the data set, which is depicted as this very fat cylinder here. And the second part is a small fraction of the data point that can have labels. And here label is some noisy observation of the underlying abstract reward F. And here epsilon is some like light-tailed observation noise. In addition to assume the partition of the training dataset, we also assume that this X as our generated solutions lies in the unknown linear subspace. And here linear subspace is described by a matrix A, and here matrix A should be considered as a very tall matrix. And here capital D can be much larger than the intrinsic dimension of the subspace, small d. And Z is just some like latent variable. So to give you a concrete example of this problem setting, suppose we have a large collection of unlabeled protein structures that's generated. And only a few has like measured properties, because measuring those properties needs some wet lab test, and it's very time consuming and expensive. So the goal is to generate new solutions that satisfies the linear subspace constraints and also can achieve large reward if we measure the by function f. If we are familiar with bandit problems, then this is basically a setting of the off-policy bandit problems with intrinsic structures. So we propose the following algorithm to generate new solutions. The first step is try to do the reward learning. And the second step is we will try to pseudo-label our unlabeled data points so that we can train a conditional diffusion model where this conditional diffusion model can take some targeted reward values. And the last step is we will generate new samples by conditioning on, suppose we want to achieve reward equal to value A, or suppose we want to achieve reward larger or equal to A, then we generate a new collection of samples. And those generated samples are expected to achieve, for example, reward larger or equal to A. But the question remains, how can we choose this reward A? Can we be really aggressive or can we be really greedy? So for example, to choose this A very large, does the conditional generation possible? And let me give you a very toy example. Suppose I have a 2D data set, X, and X lies on a one-dimensional subspace, which is represented by Z, and the transformation is 1, 0.5 times Z. And we also associate a linear reward y equal to 1, 1 transpose x plus some observation noise. And that observation noise is assumed to be Gaussian. So we collect 500 training data points. And the reward distribution of the training data point will be something like the following histogram. We see that the reward coverage is about from -4 to 4. And anything beyond 4 or -4 is not seen in our training data set. Now we train our conditional diffusion model using the previous 4 steps, and we actively choose the targeted reward value y equal to A. And here, as the first example, we choose A to be 0.0, which is about in the middle of our training data set. Then we can generate this orange population. We see that this orange population has a relatively good concentration around the underlying manifold or the underlying subspace of our data. And the reward achieved by this population is also approximately 0.0, although we have some like variability. Now we are pretty happy with the generation, so we try to increase our targeted reward a little bit, like 2.0. We see that the generative population shifted upward. That indicates that we are achieving better reward on average. And we also see that this generative population also has a relatively good concentration on the linear subspace. So its basic says, okay, choosing y equal to 2 could be possibly achieving both goals of the conditional generation to optimize, to generate samples that has large reward, and also try to preserve the data fidelity. But if we increase our reward larger and larger, then the story will be slightly different. So here we choose y equal to 5, which is beyond the range of the training data. We see that the span of this generative population is actually much larger compared to the previous two cases. And we will also see that this population actually deviates from the linear subspace much heavier compared to the previous two populations. If we increase even further on the targeted reward value, for example, y equal to 8, which is almost twice as the largest reward seen in the training data, we see that this deviation from the linear subspace is more significant. And also the generated samples has a large variability in its reward. So this basically says, okay, if we are very greedy on the generated samples quality, then we can potentially result in some failed cases. And the reason underneath is because our training data only has information up to reward about 4 or 5. So asking the model to generate samples conditioned on y equal to 8 is actually very difficult for the model to generate because of the insufficient high reward coverage in the training data points. And this can be described explicitly using the following theorem. So suppose we measure the gap between our targeted reward A with the average of the generated samples. If this gap is very small, then we say that the conditional generation model is very faithful to our guidance. And here I list several error terms that will lead to an upper bound on the suboptimality gap here. So first of all, we estimate our reward function. And we also train our conditional diffusion model. Then, of course, there are some statistical errors in these two types of the training. But what's more important is the coverage measure of your training data, which are translated into two distribution shift coefficients. Number one is the reward distribution shift, and the second one is the diffusion distribution shift, which all cares about what is the data coverage in those generating scenarios. So we have the following theorem says the suboptimality gap will be upper bounded by this very complicated equation. And let me explain a little bit. So first of all, there are actually two terms. Number one is this term in the orange box, and the second one is the term in the blue box. And usually the unlabeled data point is much larger than the labeled data points. So we can just forget about those terms that's dependent on the unlabeled data points. So the dominating term is typically the first one. The first one actually has two quantities. The first square root is actually the distribution shift, and the second square root is the estimation accuracy of the reward function. So if you are familiar with the off-policy bandit learning literature, then we see that this bound actually achieves the optimality of the off-policy bandit learning. We can also extend this to non-parametric settings, and we have two types of distribution shift coefficients denoted by kappa 1 and kappa 2, and we also have the corresponding estimation errors for the reward and for the diffusion model. So let me quickly summarize the advantage of generative optimization in the offline setting. So we achieve the optimality, and the generative samples can be of high fidelity to the subspace structures and can be extended to manifold structures. And the learning is free of the curse of dimensionality because we see the dependence is on the intrinsic dimension small d, but not on the ambient dimension capital D. So let me again pause a little bit to see if you have any questions in this like offline settings. All right, okay, perfect. Well, so in this offline setting, we already see, yeah, are there one question? Okay. Yeah, so feel free to interrupt me if you have any questions. Okay. So in this offline setting, from the toy example, we already see that, okay, the data coverage plays an important role. And if our initial training data is of relatively low quality, then there's actually no good expectation on we can generating very good samples. Therefore, this online method try to solve this limitation. So suppose we can, in the offline setting, so we generate a new population, and then we evaluate the properties of this generated new samples. And this evaluation can be, for example, evaluate the reward value of the newly generated samples, or maybe we can also take gradient information of the newly generated samples on the reward function. And regardless of the form of the evaluation, we can incorporate those new information into the conditional diffusion model that we trained on the training data. And we call this fine-tuning. So in order to make the fine-tuning computationally cheap, we don't want to train the model from scratch every time. So we want to use some guidance to adjust a pre-existing score function. So now the question comes from, okay, what is a good form of guidance? How can we ensure that it is computationally cheap? And can we also provide theoretical guarantees that the generated samples can align with the two roles of the guidance to optimize the reward function and to preserve the data fidelity? So there's existing methods using the stochastic control ideas, and those stochastic control ideas are very nice in mathematical formulations and also provide theoretical guarantees. However, the computational cost is usually relatively high. Well, so let me try to just throw something in your face. And this is our choice of the gradient guidance. And this quantity will be added to our pre-trained score function. But I don't tell you anything about how we come up with this gradient guidance. So let's build it one step by one step. Suppose we consider a very simplified case where data x is a Gaussian and the reward function is linear. Suppose our reward evaluation is noisy, the y is fx plus some Gaussian noise. Okay, so in this case, we can try to calculate what is the conditional score function, which can be represented by a clean data score plus some gradient log pty given xt. Because we specified this very precise reward model, we can find explicit forms of those of this blue guidance term. And it appears that this guidance term is minus some variance term to the inverse times gradient of y minus g transpose expectation of x0 given xt. Well, so we here see a close match of our definition of the gradient guidance to a explicit calculation in this very special case. So this kind of like acts as a very sanity check to make sense our gradient guidance. But however, I don't tell you anything about beyond this linear reward and also beyond this Gaussian design. So the idea of gradient guidance is actually the following. So suppose when we generate new samples at time x, at time t, we are at point xt. Now we look at what are the expectation of generating clean data points, which is expectation of x0 given xt. And in order to measure the quality of the generated samples, we can have this reward function at the mean of the generated samples. And we locally using this linear approximation to the reward function. Here we evaluate the gradient g at the reward function evaluated at our expected generated clean data points. So here we also specify that, okay, suppose our target reward is y. Then currently we are at the bottom broken line, and the targeted reward is actually the upper broken line. So we have a gap, and I call this gap the look ahead gap. In order to make this gap small, we need to move towards upward so that we can make this gap small. And this can be possible if we push this xt upward by some gradient. And this gradient is just the gradient of the look ahead gap, y minus g transpose expectation of x0 given xt. Well, if we can successfully push our generated samples towards the upper black dot, then if we evaluate the reward on the mean of that generated population, we see that the average reward improved to the red point. And we can continue this process iteratively so that the reward of the generated population can be higher and higher. But this also indicates that, okay, if we naively using gradient of reward function evaluated at every point xt along the sample generation, this won't work. And the reason is the reward will only be evaluated on the clean data point. There's no way that we can evaluate the reward of intermediate data points. There's actually another good advantage of this gradient guidance, and this corresponds to the second row of the guidance. I claim that gradient guidance can preserve the subspace structure or data fidelity. And the reason is this expectation can introduce naturally a projection onto the data manifold. So if we consider this if we consider a very simple situation which we depicted in the right bottom figure. So if using the gradient guidance, we can generate samples very close to the subspace. However, if we use the naive gradient f of xt, it will deviate heavily from the subspace. Okay, so here I kind of like try to convince you that the gradient guidance is actually some correct form to use so that we can achieve the two roles of the guidance, to optimize and to preserve data fidelity. But there's actually an issue with the gradient guidance because this conditional expectation x0 given xt is unknown. However, using tedious formula, we can relate this conditional information, a conditional expectation, to the score function. Therefore, we can implement this gradient guidance relatively cheaply by calling the pre-trained score function or the pre-trained diffusion model to generate clean data. And let me comment a little bit on the choice of the beta t. So we can think of this beta t as a tuning parameter representing the step size of how greedily we are adjusting our generation towards the targeted reward level y. So the overall algorithm will look something like this one. So we start with a pre-trained diffusion model, and then we try to compute the guidance by first generating some new samples and evaluate the gradient, and then add it to the pre-trained score, which is S theta plus G. And here G is the guidance. So after iterating this process for k times, we can generate a new samples coming from a fine-tuned diffusion model, supposedly preserving data fidelity and achieve great reward. And this is confirmed by the theory, which says, okay, if we run the algorithm for k iterations for a concave and L-smooth reward function, then the generated sample has a mean mu k that achieves a very close reward towards the optimal of a regularized form. And this regularization is actually induced by the pre-trained diffusion model. And we also see that this convergence is actually linear, and it will also has intrinsic dimension dependence of small d instead of capital D if data has linear subspace structures or manifold structures. Well, maybe you are not very happy with this type of like regularized convergence. we actually have this like unregularized convergence that converge to the global optima of the reward function. Well, the algorithm is slightly different compared to the previous one. However, the only difference is the first block in the broken box, which says, okay, we are now not keeping our pre-trained score function unchanged. We are also changing our pre-trained score function a little bit. And the theoretical guarantee will be something like this one. If we allow some adapting of the pre-trained model, then we can achieve the global convergence. And this global convergence is convergent at a sublinear rate, and it also has the intrinsic dimension dependence, and the generated solutions can preserve the subspace structure. So to give you some like direct sense of the two methodologies, I have this very simple simulation results. We have a reward function, which is convex, concave, sorry, and the ambient dimension is 64, and the intrinsic dimension of the subspace is 16. If we don't adapt the pre-trained score, then we can achieve some optimality, a conversion to some level that's away from the global maximum. However, if we allow some adaptation to the pre-trained score function, then we can achieve the global convergence. So in image generation, we can also observe some similar phenomenon. So by specifying different targeted reward y equal to 2, 4, 10, we can achieve potentially better and better quality the reward images. And from a visual perspective, we can see that we start with some like low reward image, and the high reward image is kind of like a more abstract and more artistic styles of the image. So to quickly summarize what I have talked about, so I present methodologies for adapting diffusion models to some abstract reward functions describing the downstream task objectives. So we establish methodologies of design reward that can be computationally cheap and can also achieve convergence guarantees on the reward function. There are many open directions in terms of this study. For example, we can consider like human preferences instead of real valued reward or gradient feedback. We can also consider the feedback being noisy or sometimes being adversarially perturbed. And we can also extend our study to the reward function being non-convex or non-smooth. So thank you for your attention, and I'm happy to take any questions.
Hi, Minshuo. Very interesting talk. Can you hear me?
Yes, yes.
Okay, so I have a question about your target reward y in your gradient guidance.
Yeah.
So here my understanding is that this y should be such that, so it's a target reward such that it should be equal to f of x. But then when we set the value of y in your algorithm, so is this y fixed, learned, or tunable?
So this y can be tunable. So because we don't know what are some like maximum value of the reward function, we can start with some conservative y's. But the hope is we can adjust the values of y becoming larger and larger so that we can generate better and better quality samples.
Okay, got it. So it's a hyperparameter.
It can be viewed as a hyperparameter. And so in this theorem, actually, we can say that there exists a sequence of yk, and the value of y depends on the iteration, so that we can achieve this linear convergence.
Okay. Okay, great. So that clarifies. I have another question about so in the for the pre-trained model. So is the pre-trained model entirely trained on unlabeled data?
Yes, the pre-trained model can be trained on unlabeled data, or the pre-trained model can be trained on some like very randomly quality data, or like low quality data.
And so if your data set also have labeled data, so the labeled data only enters the gradient guidance step.
Yes, yes.
Okay.
So yeah, typically the gradient guidance is evaluated on new generated data points. So here
Okay.
from this algorithm box, we can see that the pre-trained diffusion model is just providing a base of the guided diffusion. And we adjust the score function as theta by our gradient guidance to generate new samples.
Okay. Then, so because the pre-trained model is entirely trained on the unlabeled data,
Yeah.
or some other random quality data, then does that limit the optimality that you can achieve?
Yeah, that's a very good question. So first of all, if we just keep this pre-trained this diffusion model unchanged, then we can only converge to some like regularized optimum. And this regularized optimum is regularized by the pre-trained data. So we will see that this regularizer is our deviation from the mean of the pre-trained data, and then evaluate this deviation under the covariance of the pre-trained data.
Got it.
However, if we allow some adaptation on the pre-trained diffusion model, which is using this box, then we can achieve the global convergence.
Got it. Okay, so this is an adaptive approach that
Yes,
allows you to achieve the global maximum.
correct.
Okay, great. Yeah, okay, that's my two questions. Very interesting talk.
Thank you.
Let's see if there are any additional questions from the audience.
Right, thank you for your presentation, Minshuo. I learned a lot from your talk. And I just have a question because for the conditional generalization models, there are also the model-free method to get the generation, right? So I guess for the optimization or control problems, because we have the model, we have the optimization model, so we always take the model guidance method. So I'm wondering that if we are dealing with some case that the reward model or the optimization model is unknown, do you think we should learn the model first, or we can just directly perform a model-free generative model? Which one do you think would be better?
Well, I guess so for model free, when you talk about model free, it's kind of like we cannot evaluate the quality of the generated samples, or we cannot
we don't know the model information in the setting, and we cannot evaluate the performance.
Oh, it's kind of like maybe we cannot get any feedback of the generated samples, but we still want to generate something aligned with.
We should be able to get some feedback, like we have a reinforcement learning setting.
Yeah. So I think this is relevant to like the last open question I'm writing here. So potentially there's like maybe no reward gradients. Potentially maybe we can only get like some preferences information, or we can only get some like zeros order information like the reward value. It won't tell you us how can we compute a gradient guidance, but I would still recommend using the guidance type of methods to do the fine-tuning of those models. And I guess you have raised a very good point. So we can view the sample generation of diffusion models as a very long MDP. And the score function is actually the policy of this MDP. So using some human preferences or some like maybe some direct evaluation, although we don't know like the reward model, we can try to adjust the score function as a policy learning.
I got it. So we can still use the framework you propose for the guidance, right? We can first
Yeah, so I totally believe that. Well, so yeah, my very like preliminary idea is we can replace this guidance G by some maybe estimated guidance using some like direct feedback.
Yeah, got it. Very good perspective. Thank you.
Okay, that seems to be all the questions that we have.
Can I ask just one more quick question? So, excellent talk. So I was just wondering if, let's say we don't want to update the model or train or fine tune whatever, change the model ways. We just want to use the model, and we have some, let's say have some guidance during the inference. So is it in this case, do you have any thoughts about how we can incorporate the guidance into the inference process without update the model?
Yeah, so actually, this gradient guidance does not update your pre-trained model. So this is just a complete like additive quantity.
Okay.
So if you see from this algorithm, so this is a complete additive quantity. And once we add this quantity to the pre-trained model, we keep every parameter in the pre-trained model unchanged. And using this, we can generate new samples. I guess I don't know if this answers your question.
Okay. So
the other ones, so we want to achieve, for example, the global maximum, then we need to like slightly adapt this pre-trained model a little bit. I guess that's something you mentioned. We actually change some parameters in the pre-trained model. However, for this one, we keep the pre-trained model unchanged.
I see. Thank you. Yeah, I'll look at the paper in detail. Thanks.
Thank you.
Okay, great. I think that covers all the questions from the audience. Thank you so much, Minshuo, again, for your time and for the very nice presentation. We've all learned a lot from you. So for the remaining audience, so that our next SNAPP seminar will be in 2 weeks' time on April 28th. Okay, great.
All right, so thank you. Thank you, everyone, and thank you for the invitation.
Yeah, for sure.